it's time to discuss the last section in chapter 5, our chapter on integration. In this particular section, we're going to deal with integrals of inverse trig functions. Now, we've dealt with the inverse trig functions before, and they're generally rather complicated. Remember that inverse trig functions have a very restricted domain in order to make them a one-to-one function. We always have to take this domain into account when we're dealing with these functions. For example, arcsine, or the inverse sine function, is defined between negative pi over 2 to pi over 2, including both endpoints. However, if we want to take a look at, say, arctangent, it's negative pi over 2 to pi over 2, and we don't include the endpoints where it's not defined. Again, arc cosine is defined between 0 and pi, including the endpoints. But arcsecant is defined from 0 to pi over 2 and pi over 2 to pi, omitting pi over 2, where secant would be, not defined. When we're dealing with these functions, remember that the derivative of them actually gave us rational functions, or the fraction with a radical in it. The derivative of the arctangent of x was 1 over 1 plus x squared. Remember that when we're doing this, we're going to be undoing that derivative operation, which means in the beginning, the integrand function will not look like a trig-related function. Instead, it will be either a rational function or it will be a fraction with a radical in it. And under the radical, we'll have two terms, either added or subtracted together. We have only one learning objective in this section, which is basically to learn how to integrate these inverse trig functions. I'm going to go ahead and share my screen with you now so we can get started. You'll be happy to know this will probably be another short video. Let's go ahead and review the derivatives of the inverse trig functions. We're going to deal with the primary three, arcsine, arctangent, and arcsecant. Again, you can write it with the inverse notation, but it does not mean to raise it to a -1 power. That would give you the reciprocal. That would be the reciprocal functions, cosecant, cotangent, and cosine. And that's not what we're looking for. We're looking for the function that undoes the trig function. In other words, we're looking for the angle the sine gives us u. I prefer the arc form of the inverse trig functions. The derivative of the arcsine of u is 1 over the radical 1 minus u squared times the derivative of u with respect to the independent variable. Derivative of arctangent is a rational function, 1 over 1 plus u squared du dx. Arcsecant is the only one that has an absolute value in it. And it is 1 divided by the magnitude of u, or absolute value of u, times the square root of u squared minus 1 times du dx, the chain rule built into it. Notice that when we're looking at these primary three inverse trig functions, that we have only one that has addition between the two terms. That's going to be tangent. I remember that by thinking of the plus sign as a t for tangent. So this is going to give me the derivative of arctangent as this rational function. When I think about the arcsine and arcsecant, they both start with s, which means subtract. So I associate those two with the subtraction. You're going to have to memorize which one has a constant first and then subtracting a variable related expression, and which one has the variable related expression, then subtracting the constant. In general, what I do is I've memorized that arcsine is always 1 minus. And it's easier for me to remember that because I know that it's 1 minus cosine squared gives me sine squared. So that's how I do it, but you'll want to find your own method. Now that we've talked about the derivatives, and I've kind of reminded you, we now want to go ahead and take a look at undoing these. If we're going to undo them, then we're going to start with the integral of either the rational function for arctangent or the fraction with the radical in the denominator for arcsine and arcsecant. When we're looking at these, notice that the format of the integrand on the left has an a squared. We always assume that a is positive, and a is going to be a constant. It cannot be 0, or it wouldn't be an inverse trig integral. A is strictly positive. And then when we integrate du over the square root of a squared minus u squared, this a squared may not, in fact, be 1. It could be 4, in which case a would be 2. And then we get the arcsine of u divided by a, where a is strictly positive, plus a constant. When we're looking at the indefinite integral of du over a squared plus u squared, again, the u may be some expression involving the variable x. A may not be 1. In that case, we get 1 over a times the arctangent of u divided by a, all plus c. And again, we assume that a is positive. When we're looking at the integral of du over u times the square root of u squared minus a squared, notice that we have this extra factor of u outside the radical. Whatever u squared is, the square root of it, the principal root, must be attached on the outside. If you have it, but not the right constant, you need to multiply by a form of 1, so that what is here is exactly the principal root of u squared. And again, we considered a to be positive, and you get 1 over the absolute value of a, or a, times the arcsecant of the absolute value of u divided by a. Now, u will be an expression involving the independent variable, often x, and this absolute value cannot be dropped. All 3 of these are indefinite integrals, so they're good up to the constant plus c. Now, different professors do it different ways, but I don't expect my students to memorize these. We will actually learn a method in Calculus 2 where you'll be able to find what these are equal to without having to memorize them. But I will warn you that the method is long, difficult, and complicated. So you may prefer to just memorize them. But to be frank, I never have, and I probably never will. Let's now talk about choosing that correct formula, given the ones that we have. The first thing you want to do is you want to look at the denominator to see whether you have a difference of terms or a sum. It's going to be very similar to the derivatives. If you have a difference in the denominator, you have subtraction, then it has to be their arcsine or arcsecant. These on the left do not look like they're related to trig functions. It's only in integrating them that we get the inverse trig function. How do you know that it might be inverse trig? Well, it looks like something you might be able to use the Pythagorean theorem on. Something squared minus something squared, or something squared plus something squared. In those situations, you may want to think about using an inverse trig integral. Once we've decided whether we have a difference or a sum, we'll be directed to one of the formulas. When we have a difference, subtraction, it's either arcsine or arcsecant. If we have a sum, it must be arctangent, T for plus sign. Once we look at that, let's say that we first noticed that we had a difference of terms. Then we look to see whether it's the constant term minus the variable term or the variable term minus the constant term. This separates arcsine and arcsecant. Remember that arcsine is constant minus variable, and arcsecant is variable minus constant. Make sure that you know which one you have. Then we'll do a u substitution on the variable term, letting u be the square root, the principal root of that variable term. If instead we have a sum of terms, we have an addition in the denominator, then we probably have arctangent if one is a constant term and one involves the variable. There's generally not a radical, but there can be, so don't use that to decide that it's definitely not arctangent. It could still be arctangent. We will do a u substitution on these as well. If it is a value that is a definite integral, you may want to change the limits of integration. But I will be honest with you that these tend to be more difficult, complicated problems. And there are times when I actually don't change the limits of integration and back substitute to the original variable. It can be done both ways, and both ways are correct. Use the one that makes the most sense to you for that particular problem. Notice that when you're deciding on these formulas, you're going to have to figure out what a squared is, what a and the absolute value of it is, what u squared is, what its absolute value is. You will also have to substitute for the differential dx in the original problem. When we're looking up here, notice that all of these formulas are written in terms of du. But that means that the original was probably the differential dx. And we used our definition of u to solve for dx and substituted in to get the differential du. Typically, when we start, we do not have du as the differential. We're now ready to go ahead and take a look. When we're going to look at this, we're going to have all of the formulas so that you can practice choosing the right one. Let's look at example 1, which is an indefinite integral. We have the integral of dx over the square root of 1 minus 16x squared. Notice the differential is dx, which is not the principal root of 16x squared. We do not, in fact, have du. What we have is the original differential dx. We'll have to change that in order to be able to complete the problem. Looking at what we have, I see that I have subtraction, and this does look like something that would be involved in a Pythagorean theorem. So I'm thinking, inverse trig. The subtraction leads me to arcsine or arcsecant. Constant minus variable related expression must be arcsine. Now that I know I have arcsine, I'm going to be directed to use the first formula that you see up here at the top. I've selected this as the appropriate formula. Now I have to find something to relate the original integral to the formula. I have dx. I need du. So I'll have to take the derivative of u once I've picked it. Looking at the formula, I have a squared. A squared represents the constant term. My constant term is 1. So I go ahead and start substituting for each piece. A squared equals 1, which means that a equals 1. Remember that a is equal to the principal square root of 1, which is positive. Then I look to find u squared. U squared, according to the formula, does not include the subtraction. Subtraction is outside of u squared. So u squared is the variable term without the negative. U squared must be 16x squared. And again, I'm going to take the principal square root of u squared, which is equal to 4x. Now, the next thing I'm going to do is I'm going to identify du. Since this is going to give me u, then I can take the derivative of u with respect to the original differential dx, and this would give me 4. And I abuse the notation by swinging the dx around to get 4 dx. And after I've abused the notation, I can divide by 4 to solve for dx. Now I have something that I can substitute in place of dx in the original integral so that it will look like the formula that I have circled. Now I'm going to rewrite the original integral in the new format. So the integral of dx over the square root of 1 minus 16x squared becomes the integral. Replace the dx with du divided by 4, and you can write it to the side. And inside of the radical, you can replace the 1 with a squared. And you can replace the 16x squared with u squared. Now it looks almost identical to the formula, except it has the factor of 1/4. That can be pulled out of the integral to the front until it matches exactly. Make sure that you have substituted out the original differential dx in terms of du. Now that I have this, I get 1/4 times the arcsine, and in parentheses, I'm going to have u, which is the principal root, 4x, divided by the absolute value of a, which is 1, plus a constant. And again, you may say, well, the constant should be multiplied by 1/4 as well, and you're right, except that 1/4 times a constant is still a constant. So we say we're going to roll it into plus c. I would go ahead and rewrite this one as 1/4 the arcsine of 4x plus c. This will be your final answer. Now, you may be worried about the fact that we have this 4x in there. Notice that the formula does not put u in absolute values. Arcsecant does, it has to, but arcsine does not. Let's go ahead and turn our attention to example 2. In example 2, we again have an integral. We have the differential dx. We have subtraction, so I know it's either arcsine or arcsecant. It does indeed look like a Pythagorean theorem related thing. Got 9 minus x squared. Even if the 9 is not a perfect square, realize that you can always write it as a square by taking the square root of its squares. So even if it's 5 minus x squared, you can still use these formulas. It's just that a would be the square root of 5 instead of some other value. Looking at this, the difference leads me to arcsine and arcsecant, but I have a constant minus a variable thing. Because I have this constant minus variable thing, I know it's got to be arcsine. Since it's arcsine, I'm going to use the first formula, so I have to find my pieces. A squared is equal to 9, and I take the principal square root of 9 to get a, so a is equal to 3. Then I set u squared to be the variable term, in this case, x squared. Notice that u is not the variable term. It's the square root of the variable term, but the principal square root, and we don't worry about absolute values. In this case, we get that u is in fact equal to x, and we take the derivative with respect to the original differential, which gives us 1. We abuse the notation by swinging the dx around to the other side. This gives me something that I can substitute in place of the original differential dx in the revised integral. Now I'm going to write it with respect to u. The original integral dx divided by the square root of 9 minus x squared becomes the integral of du divided by the square root of a squared minus u squared. This looks identical to the formula, so I apply the formula to get arcsine of u, which in my case is x, divided by a, which is 3. And I add a plus c. Notice that because it's an indefinite integral, we are returning to the original variable. So we do have to go back to x. We cannot stick with u. So my final solution is simply the arcsine of x divided by 3. If you wanted to evaluate, you would first substitute a value for x divided by 3 and then apply the inverse trig function. Remember that you have to apply the order of operations. Let's now look at example 3. In example 3, I have an indefinite integral of dx divided by the quantity 25 plus 4x squared. I have two terms in the denominator, and I've got a 25 and a 4x squared, which does sound like some Pythagorean theorem related thing. So I'm thinking inverse trig and look to see whether I have addition or subtraction. They're usually in the denominator, but I will warn you in calculus 2, you might actually see one of these in the numerator. You can still apply the functions. When I'm looking at this one, what I'm going to do is I'm going to write this as 5 squared plus 2x squared. What I'm doing is I'm representing that denominator in terms of a and u. Because I have addition, I know it's not going to be arcsine or arcsecant, which requires subtraction, S for subtraction. The plus, T for arctangent. So I'm thinking this is arctangent. Again, in the case of arctangent, it doesn't matter whether it's the constant term or the variable term first, because addition is commutative. I go ahead and write down that a squared is 25, and this implies that the principal square root is 5. U squared is 4x squared, and again, I'm taking the principal root. So this gives me that u is equal to 2x. Then I take the derivative with respect to the original differential dx. Du dx gives me a 2. Then abuse the notation and swing the dx around. After the abuse of notation, in this type of problem, you typically do want to solve for just the differential dx. In this case, it would give me du divided by 2. Once I have that du divided by 2, I'm ready to go ahead and substitute. It's an indefinite integral. There are no limits of integration. Let's go ahead and circle the formula that we're going to be applying. I'm going to rewrite the original and substitute for each piece so that I can get it to match exactly the formula. I replace the dx with a du divided by 2, but I'm going to slide my 1/2 divided by 2 out to the front. Yes, it's okay to do that all in one step. I replace 25 with a squared and 4x squared with u squared. Now I have 1/2 times the formula for arctangent inside the indefinite integral. I go ahead and apply the formula, which tells me to take the 1/2, which I already have here, and multiply this by 1 divided by a, which is 5. Then I'm going to multiply that by the arctangent of u divided by a. U is 2x and a is 5. Last, I add the constant of integration onto the end. Now, you probably do want to go ahead and multiply together the constants to get 1/10 the arctangent of 2x divided by 5 plus c. Remember that the 2x divided by 5 is inside the inverse tangent. Has to be evaluated first, then the inverse tangent. Don't try to factor something out of the argument to the trig function. Let's take a look now at example number 4. In example number 4, we have another one with addition in the denominator. We've done several of these, so I'd like you to try this one on your own. Go ahead and pause the video, work it out, and turn the video back on so we can compare our results. So let's compare. I notice first there's addition in the denominator. That directs me to arctangent, which is the middle formula we have here. I look for the constant term, whether it's first or second, that's a squared. A squared represents the constant term. It's 16, so a is 4. The variable term, whether it's first or second, represents u squared. So u squared is x squared, which gives me u equal to x. Taking the derivative with respect to the original differential gives me 1, then I have used the notation by swinging the dx around. That makes dx equal to du. When I substitute, I replace the dx with du, the 16 with a squared, and the x squared with u squared. This gives me exactly the formula for arctangent. Formula tells me to take 1 and divide by a, so I get 1/4 the arctangent of u divided by a, which gives me x divided by 4 as the argument to arctangent. And I add the constant of integration. In the next example, we're going to see our first definite integral. When it's possible, you do want to switch the limits of integration. Sometimes in calculus 2, that becomes more complicated than just going back. In calculus 1, most of the time, it's still simpler to go ahead and switch completely to u. Let's go ahead and work this one together. We can see we have the definite integral between x equals 0 and x equals 2 of dx divided by the quantity 4 plus x squared. I notice that it looks like sort of a Pythagorean theorem related thing, and I have addition in the denominator, which tells me to try arctangent. When I'm looking at arctangent then, this is a plus, which directs me to arctangent. I need to find a squared, which becomes the 4, which means that a, the principal square root, is 2. The variable term replaces u squared, which means that u is x. Again, not worrying about absolute values. In the next case, we take the derivative with respect to the original differential in order to find an expression to replace the dx. This gives us 1, which we then abuse by swinging around the differential dx. So du and dx are equivalent. Next, we need to change the limits of integration. We're switching to u, and it's a definite integral, so we're looking for a finite real number, representing the net area between the curve and the x-axis from x equals 0 to x equals 2. We are not looking for the antiderivative function. In this case, when we change the limits of integration, we are again going to use our definition. We're going to use this substitution expression that u equals x. To change the limits, I write that when x equals 0, u, which equals x, is also 0. And when x equals 2, u, which is x, is also 2. In this case, changing the limits of integration didn't actually change very much. But the point is that they're no longer x values, they're now u values. And the integral would be written with respect to u, they have to match. When I write this one, and I convert, and I'm going to write x equal to emphasize that the original is with respect to x. And when I substitute the values, I'm substituting u equals 0 to u equal 2, and it becomes du over a squared plus u squared. This is going to give me, again, using the formula for arctangent, this is going to give me 1 divided by a, which is 2, times the arctangent of the expression u over a, which is x over 2, but we don't have the plus c. Instead, we need to evaluate between u equals 0 and u equal 2. In order to evaluate, we can now take the 1/2 and leave it on the outside. And instead, we can substitute the limits of integration one at a time into the argument to the trig, inverse trig function. When we do so, for the first one, we end up with the arctangent of 1. This, of course, is asking what angle between negative pi over 2 and pi over 2 has a tangent of positive 1. Since tangent's the ratio of sine and cosine, it's positive in quadrant 1, so I'm looking for the angle in quadrant 1 where the sine and the cosine give me the same value. It's got to be pi over 4. This then I can substitute in place of the first expression and turn my attention to the second one. The arctangent of 0 divided by 2 becomes the arctangent of 0. Again, we're looking for the angle between negative pi over 2 and pi over 2, whose tangent is 0. Tangent is sine over cosine. So sine has to be 0 and cosine can't be 0. Sine is 0 in that range at 0, but cosine is not. So I know that the angle here is 0. This ends up giving me the final solution of pi over 8. This is area, so I can add square units onto it. Let's take a look at the graph so you can see what this represents. Again, we took the function 1 over 4 plus x squared, and we're evaluating the area between it and the x-axis from x equals 0 to x equal 2. The graph of that is right here. I've graphed the function over the real number line, but then I only shaded the region from 0 to 2, which is this positive area that you see here in blue. The amount of that area is exactly pi divided by 8 square units. We're ready to turn our attention now to example 6. In example 6, we have an indefinite integral. In this case, we have dx divided by x times the square root of 4x squared minus 16. I notice that it looks kind of Pythagorean related under the radical. So I think inverse trig maybe. Then I notice that I have subtraction, which means arcsine or arcsecant. I look to see whether the constant term comes first or the variable term. In this case, the variable term 4x squared comes first. That must be arcsecant. That directs me to the third formula that you see. When I look at the third formula, I know that I'm going to have to replace u squared with the variable term and a squared with the 16. And I've got to have something for u. I also have to replace the differential. Let's go ahead and write down the pieces that we know. We know, for example, that the constant term is always going to be a squared. In this case, this tells us that a is equal to 4. Then the variable term is always going to be u squared, in this case 4x squared. This tells us that u is 2x. Then we take the derivative with respect to the original differential dx. Sometimes, if you want, you can actually take the derivative and abuse the notation at the same time. In other words, instead of having this interim step, you can go immediately to writing du equals 2 dx. And then we want to solve for dx. In most of these types of problems, you do want to solve for the differential dx instead of leaving it with other factors attached. This tells me that dx is equal to du divided by 2, which I can think of as 1/2 times du. Now that I have each piece, I can go ahead and rewrite the original integral. When I do so, I'm going to substitute for every piece that I see in the original until it looks exactly like the formula. Dx gets replaced with a du and a 1/2. I move the 1/2 outside the integral since it's a constant factor. Next, I have to replace the x. Coming over here, notice that I have an expression relating u and x, but u is not x. However, I can solve this for x by writing that x is equal to u divided by 2. So I'm using that substitution equation in multiple ways. Now I can replace the x with u divided by 2. The next thing I need to replace is the variable term 4x squared, which is my u squared. Then I have subtraction, and 16 I can replace with a squared. It looks almost like the formula, except for this u that's divided by 2. However, this is in the denominator, so the 2 is the denominator of the denominator, which, as you know, moves it to the numerator. This then gives me 1/2 the integral of 2 du over u times the square root of u squared minus a squared. The 2 is also a constant factor, which can come out, and the 2 and the 1/2 cancel so that I get exactly what I need. Now I can go ahead and use the formula and apply each piece back substituting to the original variables. This is going to give me 1 over the absolute value of a, and our a was 6, our a squared was 16, so a is 4. So I get 1 over 4 arcsecant of the absolute value of u, which is 2x, divided by a, which is 4, and plus a constant. In this case, I could take the 2 out of the absolute value and reduce what's inside the argument to the trig function. The x cannot come outside of the absolute value. When we apply the arcsecant here, it has to be to something that is not negative. This gives me 1/4 the arcsecant of the absolute value of x divided by 2 plus a constant. Notice that nothing that is inside the argument can come out, and nothing that is outside of the trig function can come inside. When we look at example 7, we have a definite integral again. Go ahead and pause the video, work this one out on your own, then turn the video back on so we can compare our results. Don't forget that because it's a definite integral, looking for a definite number, which means switch your limits of integration to u values as well. So let's compare our results. I first noticed that I had something in the denominator under the radical that looked like a Pythagorean identity. And I knew then, because of the subtraction, it was either going to be arcsine or arcsecant. Then I noticed that the constant term showed up first and the variable thing was subtracted. That means that it must be arcsine. And I tried to identify each piece. The constant term is always a squared. A is the principal root 1. The variable term is always u squared, and the principal root this time gives me u equals 2x. Then I took the derivative with respect to the original differential dx. Notice that I took the derivative and abused the notation at the same time to write that du equals 1 dx, since the derivative of x is 1. Now that I have something to substitute for the dx and the 1 and the x squared, I need to change the limits of integration. My limits of integration start as x values, but since it's a definite integral, I want to switch to u completely and not have to go back to x. To do that, I use the equation that relates the u to x. In this case, u is x. That means that the actual limits of integration do not change value, but they do change which variable they represent. When I rewrite and substitute the pieces, notice that I've switched from x equal negative 1/2 to x equal 1/2 to u equals negative 1/2 and u equals 1/2. It's very important that you understand that when you're doing a definite integral, you're going to switch the values from x values to u values. That means we don't want to back substitute and replace u with x. We want it to stay in terms of u so that I can substitute in the u limits of integration. Make sure you don't switch back to x and then use u values, because they're not always going to be the same. In this case, this gives me arcsine of u between negative 1/2 and 1/2, the u values. This is arcsine of 1/2 minus the arcsine of negative 1/2. Now recall that arcsine is defined between negative pi over 2 and pi over 2. That means I'm looking for angles between negative pi over 2 and pi over 2 whose sine gives me the number 1/2 or negative 1/2. Sine gives you a 1/2 when it is a long but low triangle of the 30, 60, 90 variety. Because it's the low one, this must be the 30 degrees or pi over 6. Since I know that the positive one is pi over 6, then you want to find the other one. Remember that although it is equivalent to 11 pi over 6, you cannot use the value 11 pi over 6. That's not in the interval over which arcsine is defined. It has to be an angle between negative pi over 2 and pi over 2. That means that the angle that we actually want here is the one that goes counter, or rather counter to our normal direction, which would be clockwise. This gives us a negative pi over 6 for the angle. So then we have pi over 6 minus a negative pi divided by 6, which gives us a double negative, so they add. Our final answer is that we have pi divided by 3 square roots of area between the curve of our function 1 over 1 minus x squared between negative 1/2 and 1/2. And you can see the function graphed here and the region between negative 1/2 and 1/2 shaded. This gives us exactly pi divided by, we say 3, I believe, pi divided by 3 square units of area. Let's now take a look at the next example, which is going to be number 8. When we look at example 8, we notice that this one is more complicated because it has the arcsine function in the integrand, which is not normal. We also have the 1 over 1 minus x squared under the radical. Well, how are we going to do this? When in doubt, look for a u substitution. Look for a function whose derivative or a multiple of it is already in the integrand. I know the derivative of arcsine is 1 over the square root of 1 minus x squared. So I'm going to rewrite the original integrand in terms that make it easier to see what the different pieces are. And I'm going to write it using arc notation. In this case, I know that the derivative of arcsine is related to the other factor, 1 over the square root. That means that I can do a u substitution where my u is actually the entire function arcsine of x. Let's go ahead and set up our u substitution now. I have u equals the arcsine of x. If you want to go back and review your derivative rules, you can. But in fact, when we take the derivative with respect to x, we get 1 over the square root of 1 minus x squared times the derivative of the argument to arcsine. The argument is x, so the derivative is just 1. Then we abuse the notation by swinging the differential around to the other side, which gives us the differential dx divided by the square root of 1 minus x squared. Now that we have this, we take a look at the original integral and see what substitution we can make. In this case, I'm going to be substituting u in place of the arcsine of x, the part that I've highlighted in purple. And I'm going to be taking du and replacing du with this dx divided by the square root. There's nothing left in my integrand to substitute out. This particular integral does not actually involve any of our 3 trig, inverse trig integrals. It is instead a straightforward u substitution. Do not always assume because you see something that looks like a Pythagorean theorem application that it has to involve the integral of an inverse trig function. Let's now take a look at the rewrite of this equation. We're going to rewrite the arcsine of x divided by the square root times the differential dx. We're going to replace the arcsine with u, and we're going to replace dx over the radical with du, which means that I simply have, yep, that's right, that's all I've got, u du. Since I only have u du, then I can go ahead and integrate. U is a polynomial, and I can apply the power rule. This gives me u to the 1 plus 1 divided by the new power of 2. It's an indefinite integral, so I add the constant of integration plus c. Because it's an indefinite integral, I must go back to the original variable, which is x. So I'm going to resubstitute, and I'm going to rewrite this, which is 1/2 u squared plus c, as, since my u is the arcsine of x, I can write 1/2 arcsine of x, quantity squared, plus a constant. You will occasionally see it written with the square between the arcsine and the x, but again, with functions that are already complicated, I prefer to use parentheses and the power outside because I think it's less ambiguous. Let's turn our attention now to the final example in this video. This is going to be example 9, which is a definite integral. We're looking for a constant value, which tells us we're going to switch to u completely if we can. In this particular problem, notice that we have actually 3 layers of composition. X is inside the arcsine, and the arcsine is inside the tangent. This makes this far more complicated. What are we going to choose to be our u? Look at the rest of the integrand. I have 1 over the square root of 1 minus x squared. I know is the derivative of arcsine. And because arcsine is inside the tangent, this is making me think that arcsine needs to be my u. Sometimes you just have to try it and see if it works. If it doesn't work, if you can tell it's getting more complicated, back up and try something else. It is not normal to get these right on the first try all the time. It is normal to get them wrong, have to back up and try again. So if your first attempt at u doesn't work, back up and do something else. No big deal. That's just the way mathematicians work. Let's go ahead and try now u equal to arcsine of x. Then we know that the derivative of u with respect to x will be 1 over the square root of 1 minus x squared times the derivative of x, which is just 1. This gives us that du is the differential dx over the square root. And this means that I can replace with du this dx over the square root. I can also replace u with the arcsine of x. So my arcsine becomes u. Notice I have something that's not highlighted. What's not highlighted in this case is tangent. In this case, I could switch the limits of integration, but I'm not entirely sure if that's going to help because I think I'm going to get another u substitution. But we could try it. Let's see what happens when we change the limits. If we want to change the limits, then I have to think about this equation here that u is the arcsine of x and say when x equals 0, then u equals the arcsine of 0, which is the angle whose sine is 0, but between negative pi over 2 and pi over 2. So this means that u would be the angle 0. When x equals 1/2, u equals the arcsine of 1/2, and because it's positive, it has to be in quadrant 1, the low long triangle, which tells me that u is pi over 6. Now I can rewrite the original integrand. Let's go ahead and rewrite it here. Coming from x equals 0 to x equal 1/2, I'm going to replace each piece in the original integral with the pieces that I've defined. This is then going to give me the integral from u equals 0 to u equals pi over 6. Then I don't replace tangent because it's still in there, but I do replace its argument with u. So I have the tangent of u, and I replace the differential dx divided by the square root with the differential du. This gives me the integral of the tangent of u du. Now, can I integrate tangent? Well, I don't know anything whose derivative gives me tangent directly. And I can't think of anything else to do. So let's try writing it as sine divided by cosine and see if maybe we can get a u substitution going. When we rewrite it, we're going to have the integral from u equals 0 to u equal pi over 6 of the sine of u divided by the cosine of u du. I'm looking for some kind of u substitution. And in fact, when there's no power or something being raised to a power or under a radical, or, well, it doesn't make sense, u is already simple. The argument to the trig function doesn't look like a good choice. When all else fails, look to the denominator. In this case, I'm going to try to let the cosine of u be u. But I've already used u once, so I need a different variable, but it's still u substitution. I'm going to use the variable w. So w becomes the cosine of u. Now, when I take the derivative, I want to do it with respect to the differential that is in the integral that I'm changing. So I want to take the derivative of w with respect to u. This differential has to match that differential. This is going to give me negative sine of u. And I abuse the notation to solve for dw, and I get negative sine of u du. Notice that in the integral that I'm trying to convert by doing another u substitution, I do have sine of u du, but I don't have the negative. I can multiply both sides by a -1, and this gives me that negative dw is equal to sine of u du. In this equation, I'm now going to replace the sine of u du with negative dw. And I'm going to replace the cosine of u with w. Notice that that takes care of everything that is inside of my integrand. The next thing I need to do is change the limits again, changing the variable from u to w. So I need to change my limits of integration to w values. When I look at these, I have w equals the cosine of u. So again, I'm going to change my limits of integration by saying that when I have u equal to 0, w, which is the cosine of u, becomes the cosine of 0. But the cosine of 0 degrees or 0 radians is 1. When u equals pi divided by 6, w becomes the cosine of pi divided by 6. But the cosine of pi divided by 6, being that long, low triangle, it's the x side, which is the longer side. So I get square root of 3 divided by 2. Now that I have my w limits of integration, I can replace the previous integral with w equal to 1 to w equal to the square root of 3 divided by 2. And we replace sine of u du with a negative dw. And I'm going to move the negative outside, leave the dw. And I replace the cosine of u with w. Notice that that still leaves the w in the denominator. Now you have to find an antiderivative for 1 over w with respect to w. But remember, you cannot use the power rule on this particular one, x to the -1, because it would result in dividing by 0, which should remind you that, oh yeah, this is one we know. This is the natural log of the absolute value. I know, it's a little crazy. Now we can go ahead and integrate this, and this will give us negative the natural log of the absolute value of w evaluated between 1 and the square root of 3 divided by 2. When I substitute in the limits of integration, Notice that I could take care of the negative by switching or reversing the order of the limits of integration, or I can do it after I'm done. You can do it either way, just be careful and make sure you don't lose the negative. I'm going to keep the negative large and outside and write this as the natural log of the absolute value of square root of 3 divided by 2 minus the natural log of 1. The natural log of 1, by definition, is 0. Now I need to think about what the negative natural log of root 3 over 2 represents. When I think about this, I can use algebra to split this apart because the argument has division in it. And it becomes the numerator natural log minus the natural log of the denominator. Let me go ahead and write that down. Negative times the natural log of the square root of 3 minus the natural log of 2. Now, if you want, you can reverse the order by distributing the negative to get the natural log of 2 minus the natural log of the square root of 3. You're still not done. If you want to simplify it further with algebra, you can remind yourself that the square root of 3 is 3 to the 1/2 power. And this means that we can write it as the natural log of 2 minus the natural log of 3 to the 1/2. And then we can apply log properties to bring the power 1/2 to the front, finally giving us the most expanded and simplest form that we have, which is natural log of 2 minus 1/2 the natural log of 3. This is our final answer for the area under this curve. And I'm not sure, but did I give one? I did. Here it is. So when you look at this one, you can see our original function, the tangent of arcsine of x divided by the radical of 1 minus x squared between 0 and 1/2. This area that's represented here is the natural log of 2 minus 1/2 the natural log of 3 squared units. This actually ends our study of integration. We're now going to leave studying integration and begin some of the applications of integration. What's contained in Calculus 1 and what's contained in Calculus 2 is, well, sort of up to each college and university. So I will include the next 3 sections, which sometimes are included in Calculus 1 and sometimes in Calculus 2. I also include them in my Calculus 3 or 2 playlist as well. In the next video, we're going to look at finding the area between 2 functions. In other words, we have a curve f of x and a curve g of x, and we want to know not the area between those and the x-axis, but the area between the 2 curves. Join me for the next video to see how to do that.